Osteoporosis has a multifactorial and complex pathophysiology and is characterized by a disrupted balance of bone remodeling, or bone turnover. Bone remodeling is a continuous process driven by the antagonistic effects of two bone cell types, osteoclasts and osteoblasts. In healthy individuals, there is a fine-tuned balance between bone resorption by osteoclasts and new bone formation by osteoblasts. Bone remodeling plays a key role in the maintenance of bone mineralization, structural integrity, and mechanical strength. Factors involved in its regulation include estrogen, parathyroid hormone, vitamin D, cytokines, and the Wnt signaling pathway, including its antagonists such as DKK1 and sclerostin. At the cellular level, osteoporosis develops because of an increased activity of osteoclasts, a decreased activity of osteoblasts, or a combination of these two factors. It is characterized by imbalanced bone remodeling with excessive bone resorption in relation to bone formation. This process leads to disrupted bone microstructure and decreased bone mineral density, rendering bones weaker and more fragile, and increasing the risk of fragility fractures. An interplay of genetic, environmental, and lifestyle factors may contribute to the imbalance between bone resorption and formation observed in osteoporosis. Estrogen deficiency, especially in postmenopausal women, is a major factor contributing to bone loss. Altered growth hormone, parathyroid hormone, and testosterone function may also contribute to bone turnover imbalance. Genetic factors may both negatively impact the development of peak bone mass and accelerate bone loss. Lifestyle factors, including smoking, excessive alcohol consumption, a sedentary lifestyle, and inadequate vitamin D and calcium intake, can increase the risk of osteoporosis. Medications such as glucocorticoids or protein pump inhibitors may also increase the risk of developing osteoporosis. And it has been suggested that changes to the gut microbiome may also play a role. Other factors that can contribute to an imbalance of bone turnover include impaired interactions between bone and immune cells, or an imbalance in certain proteins that promote osteoclast growth, such as Rankle proteins. Cellular senescence may also contribute to impaired bone remodeling. Cellular senescence, when living cells no longer proliferate, is driven by a multitude of factors, such as DNA damage, mutations, telomere erosion, and metabolic stress. Senescent cells may contribute to tissue dysfunction in age-related conditions such as osteoporosis. Gaining a better understanding of the molecular mechanisms underlying bone remodeling and their imbalance in osteoporosis has facilitated the identification of novel therapeutic targets for the management of osteoporosis.